Welcome to Target IES. I am Prakash Rajput and we are continuing our topic divergence. There were a few points that were left for divergence. So if I consider a point P and around this a field is like this. So what the divergence measure is how much the field is diverging from this point. How much the field is diverging from this point. Suppose my field is A vector. So here if I find divergence around this point P, it will come as positive because the field is diverging, as you can see. Now if I find divergence for this point and this field, so as the field is here is coming inside, it is coming towards the point, it will come as negative because it is actually not diverging, it is converging, so it will be negative. Now if the field is like this around the point, the field is like this around the point, so if if I find divergence for this point in this field, it will come as 0, and this is known as, now the field is known as divergence less, divergence less, or solenoidal. I can say the field is solenoidal. So these are the few things about the divergence. Now we'll move to our new topic, that is curl of a vector. So curl of a vector, curl of a vector is nothing but if I do cross product of del operator with a vector. Previously I have done previously I have done dot product with of a differential operator with a vector, then it was known as divergence. Now I do cross product of del operator with a vector field, then this is known as curl of A. This is known as curl of A. So like divergence, curl of vector also has different formula in different coordinate system. So I will write different formulas in different coordinate system. Here I am writing for the rectangular coordinates, and it is like this: ax cap, ay cap, az cap, and here it will be del by del x, del by del y, and del by del z. Now if I consider a vector has components in ax cap, ay, ay cap plus az, az cap, then I will write here the ax component, here the ay component, and here the az component. This is the formula for curl of A in rectangular coordinate system. In rectangular coordinate system. So like in rectangular coordinate system, it also has formula in divergence in the cylindrical coordinate system. I will write the formula here in the cylindrical coordinate system. So in cylindrical coordinate system, if I consider the vector to be having components arrow in arrow direction plus a phi in a phi direction plus a z in a z direction. So the formula for del cross A, that is curl of vector in cylindrical coordinate system, it will be, outside there is one component, that is 1 by rho, that is 1 by rho. Here it will be arrow cap, here it will be a phi cap, and here it will be az cap. It will come as del by del rho. del by del phi, del by del z, and here it will be a rho a phi a z. This is not complete yet. Here are some extra terms also in this. What are those extra terms? I'll write here. With a phi component, I have to multiply rho in both this a phi cap and also in this a phi cap. So this is the formula. This is the complete formula for curl of a vector in cylindrical coordinate system. Now I will write this in spherical coordinate. So in spherical coordinate system, if I consider the vector a equals to a vector, so it is having component ar in ar direction plus a theta in a theta direction. I will make it small. A theta cap plus a phi in a phi cap direction. So I'll write the formula of del cross a. Here also outside there is one term, 1 by r square sine theta, and here it will be ar cap, a theta cap, and here a phi cap. Here del by del r, del by del theta, del by del phi, and here ar, a theta, a phi, a phi. This is not the complete formula yet. There are some extra terms which need to be multiplied with theta component and phi component. And what are they? With theta, r will be multiplied, and with a phi, r sine theta will be multiplied. This is the complete formula for the curl of a vector in spherical coordinate system. Now what the curl actually means? Curl means curl basically it shows a measure of how much a field rotate how much a field rotate at any point or about any point. Rotate about any point. If I write this point here, rotate about any point. So if I consider a point here and a field like this, suppose this is the point P, and I can find here del cross some a vector. A vector is the this field vector. So I can find here del cross A, and it will tell how much this field is rotating around this point P. Now if the field is not rotating, suppose the field is like this, and I have my point P here. Now if I find del cross E, or I'll say A, del cross A, then it will come as 0. So for this field, as this field is not rotating, so del cross A will come as 0. This field is known as irrotational. This field is known as irrotational field. Also, it can be also said conservative field if the del cross A comes as 0, then the field can be said to be conservative. Now we will move to our next topic, that is Stokes theorem. So Stokes theorem states that circulation of vector field circulation of vector field A circulation of vector field A around a closed path around a closed path, suppose the closed path is L, will be equal to surface integral will be equals to surface integral of curl of A over the surface which is enclosed by that closed path L over the surface which is enclosed by the closed path or closed loop L. Suppose this is my closed path L, and it has if I calculate circulation around this loop with this path, suppose if I consider here, if I'm going, this is my small length, and find if I find circulation, for to find the circulation I have to do line integral of this closed surface. I have to do line integral of this closed surface. So I can write A dot dl. If I calculate this, then this will be same as the curl of this field over the closed surface. Now if I consider the closed surface, this मतलब कि ये पूरा surface हमारा है, ये एक small है, small area, that is ds. So to integrate it, so ds vector which is normal to the surface. So ये जो closed path है ये एक ओपन सरफेस बनाएगा, ठीक है। तो स्टोक्स थ्योरम क्या बोलता है कि सर्कुलेशन ऑफ अ वेक्टर फील्ड, दैट इज लाइन इंटीग्रल ऑफ अ वेक्टर फील्ड ओवर अ क्लोज्ड लूप or a closed path will be equal to curl of that field over the surface which you have taken as a closed path. So ये closed path है तो ये एक surface बनाएगा ही बनाएगा, तो इसके ऊपर अगर हम कर्ल निकालेंगे फिर उस वेक्टर फील्ड का, वो सेम होगा जो हम लाइन इंटीग्रल निकाला है इस क्लोज लूप के अराउंड फॉर दिस फील्ड. सो इट ऑल, सो यहाँ पर एक और चीज यहाँ पर पता चलती है कि ये जो है लाइन इंटीग्रल को सरफेस इंटीग्रल से भी रिलेट करवाता है. इट ऑल्सो रिलेट्स द लाइन इंटीग्रल विद द surface integral, line integral with the surface integral. So this is Stokes theorem. Now we will see a numerical on this and we will verify the Stokes theorem. So here is the question. Question says given the vector, this is the vector rho cos phi a rho cap sin phi a phi cap, and we have to evaluate a dot dl, we have to evaluate, and here this is vector a dot dl around the path shown. This is the path shown where this is A to B, B to C, C to D, and D to A. And we have to also verify the Stokes theorem. So how can we solve this? Let us first find A dot dl. For A dot dl, I have to consider this path. So first I have to find for AB, then from B to C, then from C to D, then from D to A. So I have to solve for every path. So I will take this figure here, and I will find A dot dl. It will be something like from A to B plus from B to C plus from C to D plus from D to back to A. So this is all I have to find for the A dot dl. So हम एक एक करके देखते हैं. Let us say for the path AB, along AB. Along AB you can see that the value of rho will be 2. The value of rho will be 2, and the differential length vector will be, as the phi is changing, differential length vector will be rho d phi a phi cap. So along AB you can see that rho is equals to 2, and the differential length vector is rho d phi a phi cap. So I will simply integrate the A dot dl, and in A vector I have to consider only phi component, because A phi dot A phi will give only the non-zero result. A phi dot A rho will give the 0, because A phi and A rho cap are mutually perpendicular to each other. So from the vector field A I will consider only the phi component, that is sin phi. So I will write sin phi, and the differential length vector, that is rho d phi, and A phi cap dot A phi cap will become 1. So the remaining thing will be rho d phi, and we know that rho is 2, and the limits for phi are from 60 degree to 30 degree. I can write it in radians, that is it is from pi by 3 to pi by 6. So if I solve this I will get 1 minus root 3. You can simply integrate. Sin phi will come as minus cos phi, and then you will put the limits, then it will be 1 minus root 3 along the path AB. Now I will solve for along the path BC. Now along BC you can see the row is changing from 2 to 5, but the phi is constant here. So the differential length vector will be here d rho a rho cap, and the value of phi we will take here will be 30 degree. So I will take only rho component from the A vector field, and rho component is rho cos phi. Rho component is rho cos phi. So I will take only rho component, that is rho cos phi, and I will use this only because the phi component will become 0. So I'll write here A dot dl will be, so the component was rho cos phi, and dl vector will be d rho a rho cap dot a rho cap will become 1, and the limits for rho are from 2 to 5. So cos phi I will write phi equals to 30 degree. So cos 30 degree will be root 3 by 2, and I can simply integrate rho d rho. It will be rho square by 2. So rho square by 2, and after putting the limits it will come as 21 root 3 divided by 4. 21 root 3 divided by 4. Suppose this is my first equation, this is my second equation. Now I will find along the path CA. If you remember the figure, along path CA. So along CA, same, the phi will be changing, and the value of rho will be 5. The value of rho will be 5. You can see along the path CD, actually the path is CD. I'll write it. Along the path CD, because I have calculated for AB, then for BC, now I have to calculate for CD, then I will go for DA. So for CD, the rho value is 5, and the angle phi is changing from 30 degree to 60 degree. So for this, the d rho, so the dl vector, that is the differential length vector, will be rho d phi a phi cap. So I can write dl vector will be rho d phi a phi cap, where phi is changing from 30 degree to 60 degree, and rho value is 5. So I can use simply the phi component as I have done for AB, as I have done for AB. So phi component was sin phi component was sin phi. So I'll write sin phi and the dl, that is rho d phi, and the values are changing from 30 degree to 60 degree, and this path is actually CD. So this will become simply integrating rho value, I will put 5, so phi will come outside, sin phi will be integrated as minus cos phi, and then putting the limits. So this will come as, for the path CD, it will come as 5 by 2 root 3 minus 1. You can simply solve this. This is third. Now the remaining path is DA, along DA. The remaining path is along DA. I'll write it here, along DA. So along DA, if I bring the figure back, so you can see that along DA the rho is changing. So the DL vector will be D rho A rho cap, and the rho is changing from 5 to 2, and the angle here is 60 degree. Phi angle here is 60 degree, which is constant. So I can use the rho component which I have used for the BC, that is rho cos phi, and the DL vector will be D rho A rho cap. So I can use the rho component only, and phi is 60 degree for the path A, for the path DA. So I can simply put the value, that is rho cos phi d rho, and rho is changing from 5 to 2. Rho is changing from 5 to 2 for the path DA. So this will come as, so if I put the value, here of cos phi, cos 60 degree will become 1 by 2, and rho d rho square by 2 after integration, and after putting the limits, it will come as, it will come as 27 by 4, sorry, not 27, it will come as 21 by 4 minus 21 by 4, because the limits are from 5 to 2. So it will come as minus 21 by 4. This is my fourth equation. Now if I add all this, this will be my total A dot dl over this closed loop L, which was given in the question. So if I add 1, 2, 3, 4 equations, so the total A dot dl will come as, A dot dl will come as, I will add all of this first part 21 root 3 by 4, second part, the first part 1 minus root 3, the first part was 1 minus root 3, then plus 21 root 3 by 4, plus third part was 5 by 2 root 3 minus 1, and the third part was minus 21 by 4. And if I solve this, it will come as 27 root 3 minus 1 by 4. This will be the total A dot dl. Now if I want to verify the Stokes theorem, now if I want to verify the Stokes, now I have to verify the Stokes theorem. For verifying Stokes theorem, I will require del cross A, and then I will do the surface integral. So del cross A, formula for del cross A in cylindrical coordinate is this. I have written as 1 by rho and all the terms, and this is my vector field. So I have to find the curl of A. So curl of A, I'll write here del cross A, it will be 1 by rho outside the determinant, and here A rho cap, here A phi cap, and rho is multiplied with this A z cap, here del by del rho, here del by del phi, and here del by del z. Here the rho component which is given in the field is rho cos phi, and the phi component is sin phi, and it will be multiplied with rho as in the formula. It will be multiplied with rho. So this is the formula, and there is no no z component, so it will be 0. So I will find this determinant, but it will be, I'll remove this first. So 1 by rho. Now 1 by rho will be outside, and you can see that if I find a rho component, then I have to do del by del phi of 0, that will be 0, and minus del by del z of rho sin phi, so it will also be 0. Now I will find the phi component, so I have to do del by del rho of 0, so it will be 0, and minus del by del z of rho cos phi, so it will be 0. So there will be only z component remaining, so z component will be del by del rho of rho sin phi. So del by del rho of rho sin phi will be sin phi plus, it will be actually minus del by del phi of rho cos phi. So cos phi differentiation will be minus sin phi, so it will become plus, and it will come as rho sin phi, and the component is az cap. So I can write this as sin phi, I can take common, so 1 plus sin phi by rho 1 plus, actually 1 plus rho, 1 plus sin phi, 1 plus rho by rho and sin phi, and sin phi az cap. This is my del cross A. Now I have to find del cross A surface integral. So for that I will be requiring ds vector. For this surface, the ds vector will be in the direction of az cap outside the screen. So the ds vector for this will be rho d rho d phi az cap, rho d rho d phi az cap. This will be this I will be using for finding the del cross A surface integral. That is, now I have to find del cross A ds vector. So z component is there only, so az cap will become 1. So I will simply write 1 plus, this is integration, 1 plus rho by rho sin phi, and the ds is rho d rho d phi, rho d rho d phi, and this rho and this rho will get cancelled, and the remaining part is integration of 1 plus rho sin phi d rho d phi. So I can simply integrate this. It will be 1 plus rho integration with d rho, and the limits for d rho are 2 to 5 integration of sine phi. As these are independent variables, so I can separate the two integrals into two parts. So this will be sine phi d phi, and the limits for phi are from 30 degree. I'm writing the limits in degree, but you have to you will be very careful about the degree and the radians. So the limits are from 30 degree to 60 degree. So I can simply integrate this. It will come as will come as will come as like will come as rho plus rho square by 2. The limits are from 2 to 5 multiplied with sine phi integration is minus cos phi, and it will be from 30 degree to 60 degree. So it will come as right will come as if we solve this and put the limits, will come as 27 by 2 into root 3 minus 1 by 2. So I can write 27 by 4 root 3 minus 1. So this is my del cross A ds surface integral, and I have found the A dot dl, which was, if I show, 27 by 4 root 3 minus 1, which is same as which is same as which I have found this here. But I will show this thing, So both are same, hence the Stokes theorem is verified. Hence the Stokes theorem is verified here, because both the answers are same. We can also verify the same. Now we will see the next topic, that is Laplacian of a scalar. Laplacian of scalar. So what is this Laplacian of scalar? It is basically defined as divergence divergence of gradient of scalar. We find the gradient of scalar, then if we apply the dot product, that is gradient of scalar will be a vector quantity, so we can apply the divergence, and after applying the divergence, this can be called as Laplacian of a scalar. So if we write in del operator form, it will be something like this. If I consider the V as my scalar field, V is my scalar field. So here I have taken the gradient, and then I have done the divergence, that is the dot product with the del operator. So it can be simply called as del square V. It also has three formulas in for the different coordinate systems. So I will write the del square V formula, that is the Laplacian formula for rectangular coordinates. For rectangular coordinates, del square V will be del 2V by del x square plus del 2V by del y square plus del 2V by del z square. This is in rectangular coordinates. Now if I write the formula for cylindrical one, for the cylindrical it will be 1 by rho del by del rho, and here it will be rho del V by del rho. Rho term will be multiplied and divided, and it will be inside the differentiation, plus 1 by rho square del 2v by del phi square plus del 2v by del z square, del 2v by del z square. This is in cylindrical coordinates. Now if I write the formula for spherical coordinate system, it will be something like del 2v, wait, I will write little below, del square v will be del by del r, actually del by del r of r square, and here also 1 by r square will be there, and then again del by del r of v, that is del v by del r actually. So this is the first term plus 1 by r square sine theta, 1 by r square sine theta del by del theta, and sine theta will be multiplied, then del by del theta of v, that is del v by del theta, and the last term will be 1 by r square sine square theta, 1 by r square sine square theta del 2v by del phi square. This is the formula for the Laplacian of a scalar in spherical coordinates. Laplacian of scalar in spherical coordinate. So you have to remember these formulas to solve the problems which will come in the later stage of electromagnetic field theory course. So these are the formulas for the Laplacian of Laplacian of scalar in rectangular, in cylindrical, and in spherical coordinate system. So now we will see some important points which we have learned from the previous basics. That is, the first point is, that is, for a vector field, if I find divergence for a vector field, suppose my vector field is a vector, so if I find divergence and it comes out to be 0, then the field is known as divergence less or solenoidal. Divergence less or solenoidal. Second point, if for a vector field, if I find curl and it comes out to be 0, then the field is known as conservative or irrotational. I have told these 2 points earlier also. Irrotational. Third point, if I find Laplacian of a scalar, suppose my scalar is v, Laplacian of a scalar and it comes out to be 0, then field is called as harmonic. Then the field is called as harmonic. Fourth point, these are basically some identities. So if I find divergence of curl of vector, if I find divergence of curl of a vector, that is, if I write in del operator form, it will be something like this. It will be 0. That is, divergence of a curl of a vector will be 0. तो अगर आप डेल क्रॉस ए निकालने के बाद दैट इज कर्ल निकालने के बाद फिर डाइवर्जेंस निकाल रहे हो तो वो 0 आएगा. ये फील्ड के लिए आप चेक कर सकते हो. दिस इज आइडेंटिटी. फिफ्थ पॉइंट, if you are doing curl of gradient v, किसी स्केलर का आप ग्रेडियंट निकाल रहे हो और फिर उसके बाद उसका कर्ल निकाल रहे हो, दैट इज इफ आई राइट इन del operator form it will be something like this, because gradient of scalar will be a vector quantity and we can find the curl, so it will be 0. अगर आप ग्रेडियंट निकालने के बाद उसका कर्ल निकाल रहे हो तो it will come as 0. this is also the identity. So these are some identity. Now sixth is if I want to find Laplacian of a vector. I have done Laplacian of scalar. If I want to find Laplacian of a vector, then we can easily find that is I will write Laplacian of vector as del square. Suppose my vector as a vector. So it is basically defined as gradient of divergence of a vector. Gradient of divergence of a vector minus curl of curl of a vector. दो बार कर्ल है, ये curl of a vector. So if I write this in del operator form, it become as del square a equals to gradient. For gradient I will write this like this, and here dot product will be shown, del dot a minus del cross a. This is the formula for the Laplacian of the vector. Laplacian of the vector, it is important formula actually. So these are some basic these are some important identities which you have to learn, and that's all for today. We'll meet in the next lecture and continue.